Cosmic shortcuts, from sci-fi to science. Imagine traveling to a distant galaxy. The vastness of space is both awe-inspiring and daunting. You wouldn't want to spend millions of years in a spaceship. The sheer distance makes interstellar travel seem impossible with our current technology. Science fiction writers thought of a solution: wormholes. These fascinating constructs have been a staple in sci-fi literature and films for decades. These cosmic shortcuts are like tunnels through space and time. They offer a theoretical way to bypass the vast distances between stars and galaxies. They connect two distant points in the universe, creating a bridge that could potentially allow for instantaneous travel. Could this fantastical idea be more than just a writer's dream? Could wormholes actually exist in the real world? As we delve into the realm of astrophysics, we find that wormholes might be closer to scientific reality than we think. Researchers are exploring the mathematical foundations and physical possibilities of these cosmic phenomena. The concept of wormholes captures our imagination. It challenges our understanding of space, time, and the universe itself. It speaks to our desire to explore the vastness of space. The idea of traveling to distant galaxies in the blink of an eye is incredibly alluring. But do these theoretical objects truly exist? Are wormholes just a figment of our imagination, or could they be a part of our future? To understand wormholes, we need to journey into the mind of Albert Einstein and his groundbreaking theory of general relativity. His equations suggest that wormholes could exist, but they also present significant challenges. Einstein's theory describes how massive objects warp the fabric of space-time, creating the potential for these shortcuts. However, the stability and practicality of wormholes remain a topic of intense debate among scientists. As we continue to explore the mysteries of the universe, the possibility of wormholes remains one of the most exciting and intriguing frontiers in modern science. Tunnels through space-time. A closer look at wormholes. Wormholes are fascinating and mysterious objects that have captured the imagination of scientists and science fiction enthusiasts alike. Imagine a piece of paper. This paper represents the fabric of space-time, the very structure of our universe. Now fold it in half. By doing this, we bring two distant points closer together. Imagine a tiny tunnel connecting the two sides. This tunnel is what we call a wormhole, a bridge between two separate points in space-time. That's a simplified way to visualize a wormhole. In reality, the concept is much more intricate and involves complex physics. It's a shortcut through the fabric of space-time. Instead of traveling vast distances, a wormhole could theoretically allow for instantaneous travel. Instead of traveling the long way around, you could zip through the wormhole and reach your destination much faster. This idea has been a staple in many science fiction stories. In reality, wormholes are much more complex. They involve exotic matter and energy conditions that we have yet to fully understand or observe. They are theoretical objects predicted by Einstein's equations. These equations, part of his general theory of relativity, provide the mathematical framework for understanding gravity. These equations describe how gravity warps the fabric of space and time. Massive objects like stars and planets bend this fabric, creating what we perceive as gravity. Wormholes are essentially extreme distortions of this fabric. They represent a kind of tunnel through the warped space-time, potentially connecting distant regions of the universe. They are like tunnels connecting different regions of space-time. While still theoretical, the study of wormholes continues to push the boundaries of our understanding of the universe. Einstein's universe, gravity's role in bending space-time. In this chapter, we delve into the fascinating concept of how gravity bends the very fabric of space-time. Einstein's theory of general relativity revolutionized our understanding of gravity. Before Einstein, gravity was thought to be a mysterious force acting at a distance. It tells us that gravity is not a force but a curvature of space-time. Massive objects like stars and planets cause this curvature, altering the paths of objects around them. Imagine a bowling ball placed on a trampoline. The weight of the ball causes the fabric of the trampoline to stretch and sag. The ball causes the trampoline to sag, creating a dip. This dip represents the curvature of space-time caused by a massive object. This is similar to how massive objects warp space-time. The more massive the object, the greater the curvature it creates. Now imagine rolling a marble across the trampoline. The marble's path will be influenced by the dip created by the bowling ball. The marble's path will curve as it passes the bowling ball, attracted by the dip. This is a simple analogy to understand how gravity works. This is analogous to how gravity affects the motion of objects in space-time. Planets, stars, and even light follow curved paths due to this warping. Wormholes take this warping to an extreme, creating tunnels that connect distant points. These theoretical passages could potentially allow for faster-than-light travel, bending our understanding of space and time even further. The Schwarzschild wormhole, a mathematical curiosity. In 1916, shortly after Einstein published his theory, physicist Carl Schwarzschild found a solution to Einstein's equations that described a wormhole. This type of wormhole, known as a Schwarzschild wormhole, is a theoretical object. It is a mathematical curiosity rather than a realistic depiction of a traversable wormhole. The Schwarzschild wormhole, while intriguing, has a major drawback. It is incredibly unstable. It would collapse faster than the speed of light, making it impossible to traverse. To keep a wormhole open, we would need something extraordinary, something called exotic matter. The biggest challenge with wormholes is their instability. They tend to collapse in on themselves faster than the blink of an eye. This makes traveling through them impossible, at least with our current understanding of physics. However, theoretical physicists have proposed a solution: exotic matter. Exotic matter is a hypothetical type of matter with negative mass. Unlike ordinary matter, which has positive mass and creates gravity, exotic matter would have anti-gravity properties. This anti-gravity effect could potentially counteract the inward pull of a wormhole, keeping it open long enough for something to pass through. Exotic matter is a strange concept. It's unlike anything we've ever observed in the universe. It has negative mass, meaning it would behave in bizarre ways. Instead of being pulled towards massive objects, it would be repelled. This repulsive force could be the key to stabilizing wormholes. Imagine using exotic matter to create a scaffolding around a wormhole. This scaffolding would push outward, counteracting the inward pull of the wormhole's gravity. This could potentially keep the wormhole open long enough for a spacecraft to pass through. In the 1980s, physicist Kip Thorne and his colleagues at Caltech made groundbreaking contributions to wormhole physics. Thorne explored the possibility of using wormholes for time travel. He even consulted on the science fiction film Interstellar, which featured a visually stunning and relatively accurate depiction of a wormhole. Thorne's work reignited interest in wormholes and their potential implications. While his research is highly theoretical, it has inspired countless scientists to explore the boundaries of physics and imagine the possibilities of interstellar travel. The concept of time travel has captivated humanity for centuries. Wormholes offer a tantalizing possibility for traveling not just through space, but also through time. According to Einstein's theory of relativity, time is relative. It can be affected by gravity and motion. If we could manipulate the openings of a wormhole, we might be able to create a time difference between them. Entering one end of the wormhole could then transport us to a different point in time, either in the past or the future. The perils of wormhole travel, dangers, and uncertainties. While the idea of wormhole travel is exciting, it's important to acknowledge the potential dangers. Wormholes are highly unstable and could collapse without warning. The intense gravitational forces near a wormhole could rip apart a spacecraft or even a planet. Furthermore, the effects of time travel via wormholes are unpredictable. Paradoxes such as the grandfather paradox raise questions about the consistency of causality. The act of traveling back in time and altering the past could have unforeseen consequences on the present and future. Gateways to the multiverse. Exploring the unknown. Some theories suggest that wormholes could be gateways to other universes. The concept of a multiverse, where our universe is just one of many, is a mind-boggling idea. Wormholes could potentially connect these universes, allowing us to explore realms beyond our own. The idea of a multiverse is still highly speculative. However, if wormholes do exist and connect to other universes, it would revolutionize our understanding of the cosmos and our place within it. The future of wormhole exploration, possibilities, and challenges. The study of wormholes is still in its infancy. We are far from creating or even detecting wormholes. However, advances in theoretical physics and observational astronomy continue to push the boundaries of our knowledge. Future technologies such as advanced propulsion systems and the ability to manipulate exotic matter could bring wormhole travel closer to reality. However, overcoming the immense technical and theoretical challenges will require groundbreaking discoveries and a deeper understanding of the universe's fundamental laws. Conclusion: wormholes, a bridge to the cosmos? Wormholes remain one of the most intriguing and perplexing predictions of modern physics. These theoretical tunnels through space-time offer the tantalizing possibility of interstellar travel, time travel, and even exploration of other universes. While the realization of these possibilities remains a distant dream, the study of wormholes continues to inspire our imagination and drive our quest to unravel the mysteries of the cosmos.